Hey everybody, and hello from my hotel room. Today we're going to finish up the stuff that I recorded a couple of days ago for capacitors and continue on and start talking about electric potential and the Laplace equation. We'll see how far we get. Here we go. All right, let's begin then with our second important topic for today, which is capacitors. We'll have more to say about this on Wednesday, but I'm going to introduce the topic today. All right, so you've probably run into capacitors before. We talked about them in intro physics. We're going to do it again. The basic idea with a capacitor is suppose I have not one, but two conductive objects. All right, both of these are conductors. All right, and let's suppose that I put some electric charge, positive Q, on one of them and negative Q on the other one. All right, so I move some charge from, say, one of them to the other using, I don't know what magic trick. All right, and I want to know what the electric potential difference between these two objects is. All right, so we have electric potential VA on one of them and electric potential VB on the other one. All right, well, one piece of good news, since these are conductors, it's not going to matter which point on this conductor I measure the electric potential because it's an equipotential. It's always going to be the same everywhere, all right, on this conductor. But it's going to be different on this one. How do I find out what the electric potential is? Well, I have to do a path integral through the space between the conductors from VA to VB, and VA minus VB, all right, is equal to the integral from A to B. Oh wait, VB minus VA. Ugh. VB minus VA is minus the integral from B to A of the electric field in the area between the two conductors along that path, integrated along that. Well, that's all well and good. The electric potential depends on the electric field, but it's going to be damn hard for me to calculate the electric field in here, because while it's zero inside the conductors, it is anything but zero outside the conductors, and it could be quite complicated. Well, so it's going to be hard for me to actually do this calculation, but there is one thing that I know. I can use Coulomb's law, which says that the electric field at any one point is equal to the integral of 1 over 4 pi epsilon naught. Charge density divided by distance to my point of interest squared. Integrate that over all possible volumes. Now our hat, all right. This is the integral form of Coulomb's law. It's a mess. I don't expect to actually be able to calculate that. The only thing that I'm going to want to get out of this is not a hope of actually calculating the electric field, but just the obvious statement looking at this, that the electric field is going to be proportional to the charge density. All right, and of course the charge density is going to be proportional to the amount of charge that I put on these guys in the first place. All right, and looking at this statement, all right, you can see that the electric potential difference between these two things, all right, is obviously going to be proportional to the electric field. And so I have the difference in electric potential, the voltage difference from one to the other, is proportional to the field, which is proportional to the charge density, which is proportional to the charge itself. All right, and every step along the way of calculating those proportionalities would involve a nasty integral, this one and then this one, and be very hard to calculate. But that's not what I'm after. I'm after the simple statement that the electric potential between two different conductors is always going to be proportional to the amount of charge on each of the two conductors. All right, and that constant of proportionality we call the capacitance. All right. All right, we call it capacitance is equal to the charge that we've put on one of the conductors and taken off the other one, divided by the voltage difference, or the potential difference between those two. All right. This quantity is not going to depend on Q or delta V. It's going to be entirely a measure of the geometry of the problem. It's going to depend on the shape of both of these metal objects, how far apart they are, what their orientations are, and so on. All right. So this is the definition of capacitance. All right. Or you often will write Q is equal to capacitance times delta V. All right, the units of capacitance would, of course, be in terms of coulombs per volt. All right, and we have a special name for that. We call that the farad. All right. By the way, as a weird circumstance in the CGS system, which I haven't talked about much, centimeter gram second system. All right. You may remember that this system used a funny version of Coulomb's law that made this constant out front disappear. It turns out that if you work out this in the CGS system, the units of capacitance are the centimeter. That's it. Just it's a unit of length, which is kind of makes sense since I said that the capacitance depends only on the physical geometry and the distances between the capacitors and their shapes and sizes, and not on anything having to do with their sort of detailed electrical properties. So that's kind of an aside. All right. So the point is that the capacitance gives you a constant proportionality between the amount of charge on something and the electric potential. Now what this means is that as you move charge from one of these objects to the other, the electric potential between them gradually increases. As you move more and more charge, you get a greater and greater electric potential. And one of the uses of these capacitors is to store charge. So you can have charge moved from here to here, keep creating a reservoir of charge on this object, just in case you should need it. All right. And so when we talk about capacitance, this constant C is a measure of the capacity of this system and how much charge you can store when you add a particular amount of voltage to the device. Now, one common kind of capacitor, one that you meet almost every day, and a particularly good way to build capacitors, is to have a big flat sheet of metal, all right, as wide and as thin as possible, all right, and as close to it as you can possibly get. You have a second metal sheet, all right, which I'm going to draw like this. All right, and let's suppose that both of these sheets have a surface area A and are separated by a distance D. All right, and suppose we want to work out the capacitance of this system. Well, let's think about the charges here first. Let's suppose that the upper plate has a charge plus Q on it, and the lower plate has a charge minus Q on it. All right, and we're interested, in order to calculate the capacitance, we're going to have to calculate the electric potential difference from one of these plates to the other. Well, how are we going to proceed? Well, first, let's think about the electric fields here. All right, let's think about the electric field from the two sheets of charge that I'm interested in, the two conducting plates. Well, it's obviously going to be the sum of the electric field from each of the two plates. So let's think about the electric field from a single plate. All right, so here's my plate like this. All right. Well, what I'm going to do is I'm going to draw a Gaussian surface in the shape of a tuna can, basically, that punches through my sheet and goes out to the bottom. All right, and this problem may seem a little bit familiar, and that's because I already worked it a little while ago. When we were talking about Gauss's law, I figured out the answer to this problem already. If you can't remember it, check your notes or take a look in the textbook. It has it also already worked out. All right, so in side view it looks like this, and I calculated way back when that the electric field was pointed perfectly up and down, assuming this had a positive charge. All right, up when you're above the sheet and down when you're below the sheet, and assuming the sheet is very, very wide compared to the heights involved here, which is to say, think of it in an infinite sheet, then the electric field was constant and doesn't change for any location above or below the sheet. And the strength of the electric field was equal to Q over epsilon naught A. Whoops. Checking my answer, checking my notes, it was actually Q over 2 epsilon naught A for a single sheet. All right. The reason I messed that up is now let's think about what happens when we combine two different sheets. Okay. All right. The upper sheet has a positive charge. The lower sheet has a negative charge. All right. And so the upper sheet is going to have an electric field up. Let's call that E plus. And downward here, electric field E plus from the upper sheet. All right. And it's the same everywhere. So even when we're down beneath the lower negatively charged plate sheet, we're still going to have a downward electric field there. All right. On the other hand, the negatively charged sheet is going to have an electric field that points towards it on either side. All right. And that's also going to exist on the far side of the positive sheet as well. All right. Since the magnitude of both charges are equal, the magnitude of the electric field from the positive one is the same as the negative one, and it doesn't change with distance, so it doesn't matter how far we are, we'll always have the same electric field, which is given by that expression. All right. So hopefully you can see that above both plates, the electric fields cancel out, and we get zero field there. All right, and the same goes when we're below both plates. All right, but in between, they add together and give a electric field downward. All right, that's twice as strong as the field from a single sheet. All right, so the electric field inside the capacitor is equal to Q over twice this, which is Q over epsilon naught A. All right, so now I want to find the electric potential from one plate to the other, which means I need to do a path integral from, say, the negative charged one up to the positive charged one. All right, and that's equal to negative integral from the minus plate to the plus plate of electric field dot dl, and hopefully you can see that my integration direction is opposite the electric field. So this dot product here will have a minus sign. That's going to cancel out the minus sign here. All right. Also, the electric field is constant, and so I can pull the electric field outside and get all right. And if we integrate the little lengths of distance, we get the overall distance from one plate to the other, which is simply called d from the previous diagram. All right. And so we now find that delta V is equal to electric field inside times distance, which is, borrowing from this expression, Q d over epsilon naught A. All right. And so as promised, the electric potential is in fact proportional to the charge on the plates. All right. The capacitance is defined as the charge divided by potential. All right. And so I'll put in my expressions for each. Q over, and now my potential equation, Q d over epsilon naught A. And sure enough, the charges cancel. All right, I can take this denominator of the, take this denominator of the denominator, flip it over up into the numerator, and end up with that the capacitance is equal to epsilon naught A over D for parallel plate capacitor. All right, so this is useful. It tells you how to design a capacitor. If you want to get the biggest C possible, you need to have plates that have a very large area and that are spaced a very small distance apart from each other. All right. As I said, when you're thinking about the CGS system, all right, if you carried out the same calculation in the CGS system, your value for the capacitance would simply be area divided by distance, and the units on that are, of course, area would be centimeters squared divided by centimeters, and so it makes sense that the units would be just centimeters for CGS capacitance. For SI, you don't have this nice property, it's just farads, which is a special weird term, but fortunately every capacitor over in the electronics lab is printed with its capacitance in farads rather than centimeters, and so this is kind of the unit system that we're stuck with. In any case, now in theory that means that if you can calculate electric potentials, you can calculate the capacitance of any two objects, regardless of whether they're parallel plates or spheres located at some distance or whatever. But actually carrying out this calculation, can be quite difficult for shapes that are more complicated than what's here. Okay, so we've talked about capacitors a little bit. Let's talk about energy in capacitors, and in particular, how much energy does it take to put charge onto a capacitor? So the situation we're going to be imagining is one in which we've got two plates. They don't have to be parallel plates. It doesn't matter. All right. And at the time that we're speaking, we have a charge of plus Q on this one and minus Q on this one. As a result of that charge that's currently on there, we have an electric field pointing from the positives towards the negatives, and a voltage drop across this. All right, so what I want to do is I want to do some work on some charges and move a small amount of charge from the lower plate, which has the minus charge, to the upper plate, which has the plus charge. All right, so I'm going to move, maybe with a wire or battery, just picking them up and carrying them by hand, so, an amount of charge dq. I'm going to shift my notation here. Let's call that d little q. Let's call the current charge on the capacitor little q, right? Just so my variables match here. All right, so moving a little bit of charge dq from the lower one to the upper one. Well, how much work does that take? Well, we said earlier that the relationship between work and electric potential was that in general the amount of work to move some charge was equal to the amount of charge that was moving times the change in the electric potential that you moved that charge through. Now in our case, we have not some big charge, but a little bit of charge dq which is moving. And that's going to result in a little bit of work being done, which we'll call dw. All right, so every time I move a little bit of charge, it takes a little bit of work. And now what I want to do is imagine charging the capacitor from q equals 0 to q equals some final charge, which I'm going to call big Q. Okay, so we're charging it up to maximum, whatever that maximum might be. And we want to know how much total energy does the capacitor have, and which is the same as how much work did we put into it. Well, every time we move a little charge, we get a little work, and so the total work is equal to adding up all the dWs, which is to say that the work is equal to integral of dW, which is equal to integral from q equals 0 to big Q of delta V dq. Now what's delta V? Well, we have our equation for capacitors from before. I have it right here. This should look familiar. We were just here, although you were here 5 minutes ago and I was here on Monday. Anyway, so the relationship between current charge on a capacitor and the electric potential, that ratio is the capacitance. The capacitance is going to stay the same. And so if you look at that equation and you say, what's delta V? Delta V is equal to current charge on the capacitor divided by the capacitance, C. So let's plug that in there and end up with integral from 0 to big Q of Q dQ over C. And now we're going to carry out that integral. Integral of Q dQ is 1/2 Q squared. Evaluated between 0 and Q. So this is going to be 0. And so I end up with the work done to charge the capacitor is 1/2 amount of charge on it squared divided by C. Now that's typically not the way we do things because it's difficult to measure the amount of charge on a capacitor. It's a lot easier to hook a meter up to it and measure its voltage. So I'm going to convert this back into the voltage on the capacitor, remembering that the charge on the capacitor is equal to its capacitance times its final voltage. I'm having slightly shifting definitions of what delta V is as I go along, but that's okay. Anyway, we end up with the work done to charge the capacitor is equal to 1/2 this quantity squared CV squared. All right, so that's the amount of work required to charge a capacitor. It's also the capacitor's electric potential energy, when you put voltage in it. And you may remember from introphysics, I derived this equation there and did a fun demo where I charged it up and short-circuited it and released all that energy, and it made a big bang. So that's cool. What I want to do now, though, is compare that with a earlier result that we had from before. All right. We said that another way to calculate the energy in an electric system was to integrate the electrical energy, the energy contained in the electric field. So let's talk about how much energy is contained in the electric field here. All right, so my next goal is to determine the energy stored in the electric field surrounding a capacitor. And in particular, I'm going to be focusing on a parallel plate capacitor. This is kind of take two, so I've already written some stuff, but that's okay. So we've got two plates, surface area A, and they're separated by a distance d. We solved this problem before. In any case, several lectures ago we were talking about how much energy is stored in the electric field, and we said to get that you have to take the integral over all the volume of all of space of 1/2 epsilon naught times the electric field strength squared. All right. So what does that work out to in this particular case? Well, we have, that means, well, let's think about what the electric field looks like. We know that the electric field is equal to 0 above and below the plates. All right. So that area makes no contribution to this integral over all space energy integral. All right. But if the plates are positively charged here and negatively charged here, we're going to have an electric field that points straight down in the inside. All right. And so the electric field is going to be equal to the electric potential difference. Let's just call that V, divided by the distance over which that potential change happens, which is D. All right. And so the total volume, and the electric field is constant everywhere within that area. All right. And so what we need to do is energy in the electric field is equal to integral of 1/2 epsilon naught V squared over D squared d tau, integrating over the inside capacitor. All right, and by which I mean the volume that's contained between the two plates. All right, all these things are constant over that area. Wait, what did I write? D tau, that's wrong, just D. D squared is what that should be. All right, so in any case, I need to integrate that over the volume contained between the plates. These are all constants, and so this becomes 1/2 epsilon naught voltage squared over separation squared, integral of the little pieces of volume. So volume between plates is going to be the plate surface area divided by the multiplied by the plate separation. All right, and so that's going to be A times D, and so this here is integral of the volume over that whole volume. So that's that. All right, leaving us with the energy stored in the field is equal to 1/2 epsilon naught V squared over D times A. All right, we're almost done here because earlier we derived an expression for the capacitance of this parallel plate capacitor. I still have this listed. We found that capacitance for the parallel plate capacitor was epsilon naught A over D. All right. Well, look what I've got here. I've got an epsilon naught, an A, and a D. So that works out to be equal to a C. And that means that the energy stored in the electric field here is equal to 1/2 epsilon naught A over D capacitance times the voltage squared. All right, and make the what I'd like you to observe, of course, is that this is exactly the same as this. Whether we calculate the work done by adding up the effect of moving all those charges around from one plate to another, all right, we need this. Here we calculated the amount of work done to charge up the capacitor. This set of math shows the amount of energy stored in the electric field inside the capacitor. And of course, they're exactly the same. That shouldn't be too surprising, but it does hopefully give you a little more trust that energy really is stored in the electric field in this situation. All right, I'm going to have to look at the time, but I think that might be enough for today. And maybe on Friday I'll get around to talking about Laplace's equation. Let's see.